This is Bob McFetrich with Beckwith Electric, thanking you again for joining us on session number 3, Field Components Required for IVVC. In session number 1, we talked about the economic drivers for IVVC and why a utility may want to look at implementing an integrated volt VAR control scheme. In session 2, we talked about the need for it, why voltage fluctuates, and why it would be a good idea to try to control the amount of fluctuation so that we can control the amount of load on the system at any given time. In this session, we're going to talk about the different field apparatus components we have available to help us regulate or change the voltage as the load changes. So, as we finished up our last session, we have apparatus both within the substation fence and then downline that will allow us to vary the voltage as the load is varying. Within the substation fence, we have load tap changing transformers or bus regulators that can regulate the bus voltage. Or we can leave the bus voltage unregulated and regulate the voltage at each individual feeder using feeder regulators. We can also vary the voltage inside the fence using substation capacitor banks, although substation capacitor banks are typically there to cancel out the VARs required for the distribution transformers within the substation to make it VAR neutral to the transmission system. So typically substation capacitor banks, if they are within the system, are there normally to be controlled more for VAR flow than for voltage flow, but we can use them to regulate the voltage. Finally, outside the substation, we have single-phase line regulators and also pole-top switch capacitor banks, which may be either fixed banks, which are not controllable, or switched banks, which are. The load tap changing transformer. So, an LTC and a regulator both function in the same way. First of all, they are what we call unidirectional, in that they change the voltage only on the load side of the device. So on the source side of the device, the voltage remains fairly unchanged. Now, all an LTC or a regulator is a transformer that has taps that can be changed under load conditions. And each tap is typically going to affect the secondary voltage by 3/4 of a volt. All single-phase regulators have 32 taps, 16 raised, 16 lower, with a neutral position. The majority of load tap changing transformers also have 16 raised, 16 lower taps and a neutral. Now, some transformers may only have 16 taps, 8 raised, 8 lower, and sometimes instead of doing 5/8% per tap, they may do 1 1/4. So they may have twice as effect per tap, and therefore instead of seeing 3/4 of a volt per tap secondary, you may see 1.5 volts. But as a general rule of thumb, all single-phase regulators and the majority of load tap changing transformers allow the load side voltage to be either increased or decreased in 0.75 volt increments, with 16 increments raising the voltage and 16 increments lowering the voltage. The other way we can affect the voltage is by using capacitor banks. When a capacitor bank is closed, it will induce a voltage rise, and when it is open, it will induce a voltage fall. The amount of voltage is not consistent as it is with a regulator or an LTC, and it is determined by both the size of the bank and the relative distance of the bank back to the source. So the larger the bank, in other words a 1200 kVAR capacitor bank when closed, will provide a larger voltage increase than a 600 kVAR capacitor bank. But if we have a 600 kVAR capacitor bank and we place it right outside the substation fence, we may notice only a 0.2 of a volt rise when we close that bank. We take that same exact bank and move it 2 miles further down the system, And now when we close it, we see a 2 volt rise instead of a 0.2. And that is because the further we get from the source or the substation, the larger effect it is going to have on the voltage. So, the differences between using a regulator or LTC and a capacitor to regulate the voltages are as follows. Regulators are unidirectional. Again, they only affect the voltage on the load side of the regulator or LTC, while capacitor banks are bidirectional. When a bank closes, it affects the voltage on both sides of the bank. Secondly, the regulator can increase or decrease the voltage in multiple steps, where a capacitor bank is all or nothing. Third, a regulator corrects the voltage only. A capacitor bank, besides correcting the voltage, can also correct the power factor or the VAR flow. So we have an additional benefit with a capacitor that we do not have with a regulator. One other thing to remember though, capacitors lose the amount of capacitive rating as the voltage drops. So a 600 kVAR cap bank is not going to be 600 kVAR at lower than rated voltages. And therefore you will have less rise. So as the voltage goes lower, the effect that the capacitor bank has on raising the voltage decreases. And that's not always exactly what you would want. So, keeping all this in mind, we will start with the load tap changing transformer. The reason you would have a load tap changing transformer in the substation is typically because of space. Load tap changing transformers take up less footprint than either bus or feeder regulation we're going to be talking about next. So if we are in a metropolitan area where land is very expensive and we want to get as many transformers and feeders into the footprint as possible, we would want to use load tap changing transformers. They can also be less expensive if you have 3 or more feeders than some of the other approaches. A load tap changing transformer will typically cost between $100,000 and $150,000. So typically somewhere between 2 and 3 feeders would be the break-even point between the cost of going with feeder regulators and the cost of going with a single LTC. So the advantages are definitely that it is reduced footprint, and it may be cheaper, and it'll be more cheaper with the more feeders you have on that tap changer. Disadvantages of a load tap changer though are as follows. First of all, it is monitoring only one phase but controlling all 3. Therefore, it is assuming that the load is balanced between all 3 phases, and therefore the voltage drop would be the same. If the load is not balanced, the voltages will not be the same, and therefore if you're only sensing one of the 3, you may be sensing the low voltage or the high voltage and causing voltage complaints on the other phases. So the first disadvantage is we're only monitoring one phase but controlling all 3. This is also a disadvantage because if we have a failure in either the control or the tap changer and we go to full 16 raise or full 16 lower, we're going to negatively impact the voltage on every single customer of that transformer. So our reliability is not as great. Another issue comes in taking it out of service for maintenance. To maintain an LTC, you have to take the transformer completely out of service, and this can cause a lot of switching to be done to get the load off of that transformer and onto other transformers. A final disadvantage is a LTC is regulating multiple feeder breakers and multiple feeder circuits. Each of these circuits will have different line lengths, different loading, different impedances, and therefore different voltage drops. So you can have the case where you cannot keep one of the customers closed on one feeder below 126 while keeping a customer on a longer feeder at the end of the line above 114. So because you're regulating more than one feeder, it assumes that each of the feeders is also balanced. So not only do we want our phases to be balanced, but we need the feeders to be fairly close to each other in the amount of voltage drop. And if not, we're going to have to do downline correction to make it look the same. So if we have 4 feeders, we want each of the 4 feeders to have approximately the same voltage drop. If we have one feeder with a 4 volt drop and another feeder with a 10 volt drop, we're going to have issues. So this is how a substation would look with a load tap changing transformer. So we can see the transformer, picture of a load tap change transformers right here. These are the compartments where the mechanisms are for the actual load tap changing mechanism. And you can see that when it taps, it affects the voltage on this entire bus, and in this case all 4 feeders. So again, if this feeder's got a 2 volt drop and this feeder's got an 8 volt drop, we've got 6 volts difference. So if I raise it to accommodate the 6 volts here, and I've only got 2 here, we're 4 volts higher here than we need to be, and that could cause an overvoltage here. But if we only raise it a couple volts to do this drop, then we risk undervoltaging the customers at the low end of this circuit. So with an LTC, we really need to have all 3 phases balanced, and we need to have the circuit such that the voltage drops on each circuit are fairly consistent. Now, the next approach we can use is to go with bus regulators. Bus regulators are the most cost effective if you can use them. And what a bus regulator does is it sits outside the transformer, so it's not physically attached to the transformer, but it is regulating the bus just like an LTC. And typically this would be done with 3 single phases, so that gives it an advantage also that we're now monitoring each phase individually and we can control each phase individually. So unlike an LTC, we do not have to be balanced between the 3 phases at the bus level in order to apply bus regulators. They do require a little bit more physical space than an LTC, and we still are regulating multiple circuits with the same device, so we still need to have the voltage drop across each of those circuits be relatively consistent. But we do have the advantage that we are at least looking at individual phases. So a failure of one phase now is going to impact every customer on that phase of the transformer on all 4 circuits, as opposed to an LTC failure which causes every customer on every circuit, every phase to be either over or under voltaged. A possible disadvantage for LTC or for bus regulators is the sizing. Right now, the largest bus regulators, single phase that can be purchased, are 833 kVA, and therefore, if your transformer is too large, you will not be able to use bus regulation. And this is what a bus regulator single line would look like. So again, we have taken the LTC off. We have moved the regulators down line, typically below the load side bank breaker, so that they are not part of the transformer differential zone of protection, but they are residing on the bus, and therefore a fault in a regulator could cause a bus differential. So we have to keep that in mind from the protective side. But again, the bus is regulating all 4 circuits, but in this case, if it's a single phase bus regulator, each phase is being regulated independently. Finally, we can go with feeder regulation. With feeder regulation, we are going to move the regulators further down and we're going to place them on each feeder. The advantage is now we're monitoring every phase individually of every feeder. So if we have a control failure or a regulator failure, it's only going to impact customers on one phase of one circuit. So we're going to have the least amount of impact if something were to go wrong. A disadvantage is cost, obviously, and also space. But another advantage is now since we're regulating each circuit independently, we can have different voltage drops on each circuit and accommodate that without needing downline equipment. So the advantages of regulators are they provide you the most flexibility in controlling the voltage because now each regulator is zoned to control only one phase of one circuit. So from the LTC, it is zoned all three phases of all four circuits. Single phase bus regulators have three zones. Same phase, but on all four circuits. And the regulators, we would then have 12 zones. Each phase of each circuit would be a separate zone. So we go from one zone of regulation to 3 zones to 12 zones. And obviously with the more zones, the less customers per zone, and also the less voltage drop per zone, so we can run a much tighter voltage with that. And this is what it would look like on a single line with feeder regulators. So now the feeder regulators are below the load side breaker, so they are no longer part of the bus differential scheme, and they are actually on the load side of each feeder, and these are each individual 3 phases. So phase A, phase B, phase C are each regulated with their own regulator and their own control, and therefore a failure of one regulator or one control will only impact customers on one phase of one circuit and will not impact the remaining customers on the other circuits or the other phases. Finally, we can use line regulators, which would be applied outside the substation fence. And this would be the case especially if you're using LTCs and you have one feeder that has a much greater voltage drop than the other 3. Let's take a case where we have 3 or 4 feeders. 3 of them have 2 volt drops, but the 4th one has an 8 volt drop. If we were to place a line regulator halfway down that line, then the LTC would only be regulating the portion of the circuit up to the line regulator, which may only be a 4 volt drop, and now that portion is much more consistent with the others. The other reason to use line regulators is your line may be too long for one regulator to regulate the whole drop. If I've got 13 volts of drop and I've got to be between 114 and 126, that cannot be done. So I must take that 13 volts of drop and divide it into 2 sections, 6.5 volts per drop, and now I can keep the voltage within my guidelines. So the 2 reasons we would see the use of line regulators would be if we have an LTC at the substation and we have some lines that have greater drops than others, we need the LTC to be regulating approximately the same drop on each circuit. So if they're not the same, then we can use line regulators to make them look the same. So in this case, the LTC would be regulating this portion of the circuit, but on this feeder, the line regulator would be regulating this portion, not the LTC. On this particular circuit, the LTC would be regulating the entire circuit because there are no line regulators on it. So, if we use line regulators, the general rule of thumb is if you're only going to need one set, typically you put it about 3/8 of the line length down, because the load typically is higher in the first half than the second half of the circuit. 2 sets we would typically look at like 20% and 50%. Now, if we have a combination of either feeder or bus or LTC regulation inside the fence and regulators outside the fence, we have to coordinate them, and that is done via the use of the time delay. And why we need to coordinate them is shown on this slide. So, if we assume that we have an increase in load down here, that is going to cause a voltage drop across the entire circuit. If we were to allow regulator 2 to raise the voltage first, that would bring this portion of the circuit back into what we consider good voltage, but this portion of the circuit would still be low. Therefore, regulator 1 is going to have to raise the voltage. But when it raises the voltage, regulator 2 is on its load side, so it does affect the voltage the whole way down the circuit. So now this voltage is back in band, but now we've raised this voltage too far, and we need to send it a lower to get it back in the band. So we have corrected the voltage caused by the additional load here, but we've done it by requiring 3 operations: a raise, followed by a raise, followed by a lower. If we would have allowed regulator 1 to raise first, it could have corrected the voltage for the entire circuit, and we would have reduced these 2 operations on this set of regulators. So the general rule of thumb is you always want the regulation closest to the source to have the shortest time delay, and then you want to add 10 to 15 seconds of time delay for each set going away from the source. So if I had an LTC here at this bus and it was set for 60 seconds, I would typically set this time delay for 75 and this time delay for 90. That way, if the only low voltage were here, this would be the only one that would tap. It would take longer, 90 seconds, but it would be the only one. If the entire circuit was low, it would be corrected at the bus with the LTC having the shortest time delay, and then that would allow for these not to have to operate at all. As a final topic in this session, we're now going to look at capacitor banks, as there are other options to correct the voltage. And we can apply them like regulators either inside or outside the substation fence. Typically inside the substation fence, the capacitor banks are much larger, anywhere from 2 to 5 to even 8 megavar. And typically they're done in stages, 2 or 3 stages. So if I had a 4.8 megavar, it may be made up of 2 stages of 2.4 each. So I can close in one stage, and then if need be later, close in a second stage. Typically we're using substation capacitor banks to cancel out the impedance of the substation transformers so that we are VAR neutral to the transmission grid. It is much less expensive to have VARs on the distribution system than to have them added to the transmission system. So we really don't want to have the transmission system being required to transmit VARs to the distribution system. We would like to see the distribution system create the VARs needed for its own impedance losses. And there are only 2 ways to create VARs within the utility. One would be capacitor banks, and the other is generators. So if we do not have enough capacitance on our distribution system, the generator is going to have to provide those VARs. They're going to have to flow across the transmission system, which will cause voltage losses, and then they will have to flow through the distribution system down to the source requiring, or the load requiring, those VARs. And so you have a lot of losses. So if we can move those VARs closer to the motor loads that need them, then we can reduce the voltage losses on both the transmission and the distribution system. And so that's typically why you would see substation capacitor banks. They do have a disadvantage in that typically if they are in the same substation as an LTC, they will increase the number of operations on the LTC. The reason for this can be seen in a normal day's load. So in the morning, as the load starts to increase, we have a voltage drop, and therefore we need to raise the voltage. But we may not need 2.4 megavars yet. So instead of turning on the capacitor bank to increase the voltage, which may throw us too far leading, we're going to have to raise the voltage via the LTC. And maybe we have to raise it twice. Finally, the load increases enough to where we do need the capacitance, so we turn the bank on, and in doing so, it creates a large voltage increase, which will then drive us out of band and cause the LTC to have to reduce the voltage. So typically for every time the capacitor bank operates, a general rule of thumb is you're going to add 3 to 5 operations on your LTC, because the cap banks are so large that they have a bigger impact on the voltage. The other thing we can use is we can apply switch capacitor banks downstream. They would typically be much smaller, typically in the range of 600 kVAR, 1200 kVAR, typically no more than 1800 kVAR. And so when they're turned on, they don't have as big an impact on the voltage back at the source. And if done correctly, we can actually reduce the number of operations on the LTC by applying many smaller switch cap banks to correct the voltage as opposed to one large capacitor bank at the substation. The other advantage with having the banks downstream is if we have the bank at the substation, the VAR current still needs to leave the substation capacitor and traverse down the distribution circuit to get to the motor load that's requiring that current. And so we are creating voltage drop down that distribution circuit. As we mentioned earlier, the impedance is typically 3 to 4 times greater reactive than resistive, and therefore reactive or VAR current is going to cause a greater voltage drop. So if we move these capacitors closer to where the motor load is, then that VAR current does not have to flow through as much of the distribution system and therefore does not create as much voltage drop. So, in summary of session number 2, hopefully we have seen that we are going to have voltage variations on our distribution system. We are going to need to be able to dynamically react to that and correct the voltage as needed. And to do so, we have equipment both inside the substation and outside the substation. We can use LTCs, we can use bus regulators, feeder regulators, and line regulators, which allow us to vary the voltage in 0.75 volt increments and give us better resolution. Or we can apply capacitor banks, which don't give us the resolution but can help us in that they can help eliminate or minimize the amount of VAR current flowing through the distribution system, creating additional voltage drop. So our next session is going to now start probing how do we coordinate which device is going to correct the voltage when it's out of band. So hopefully you've enjoyed this topic, and we will see you for session 3. Again, at Beckwith Electric, we always appreciate and value your time. Thank you and goodbye.